An introduction to this video, I had recorded a podcast with Larrin back in October 2020 about his article that he had released, What is the Future of Stainless Steel Knife Design? This is actually prior to MagnaCut being released, so I thought you guys would find that interesting. I'll leave a link to this article in the description of this video, and without further ado, enjoy the video. All right, how's it going, guys? Sean here, and I'm joined here with Dr. Larrin Thomas. How you doing, man?
I'm doing great. How are you, Sean?
Hey, doing fantastic. So I thought, what would be really cool is if we can get you on a podcast and talk about it in finer detail.
Yeah, I think that's a good idea. This article was, I write a lot of very technical articles. This one got a lot more specific into steel design, which is actually my specialty. So I work in the automotive industry more, designing sheet steels for cars. So, I get all the way in the weeds on specific alloying additions. And tool steel is a lot different in terms of how you design it. But a lot of the alloying additions are similar in terms of what you're trying to do with them. And so I really wanted to get into how are we designing these steels? And not only that, but how could we design them to be better, to make them better knife steels? And I worried even a little bit. Maybe I'm revealing some secrets here. Maybe the steel companies are
Hmm.
gonna steal all my good ideas. But I thought doing the article would be more interesting and more fun. And hopefully those people already know these secrets. They're just not using them for whatever reason.
And by people, I mean, you're talking about other steel designers whose actual job is to make these types of steels that we all use? Or?
Yeah, the metallurgists who have jobs for those tool steel companies, Udahome, Bowler, Crucible, Carpenter. You could read my article and come up with an idea on a steel design. So, this is real industry insider stuff.
Yeah, so getting to your article, Laren, I mean, you basically outline there's basically big trade-offs between tool steels and stainless steels where we have different features. We can have one with stainless, but we can't necessarily have one with tool steel.
Yeah, so there's a whole range of properties that we want in a knife steel. Some big ones are hardness, which is a measure of
Mhm.
strength. And in a knife, a lot of that is how resistant is it to rolling or deforming. So, if you're cutting something, you don't want that edge to fold over or deform because then it's no longer sharp. Uh,
Yeah, that's huge.
yeah, another one is toughness, which is a measure of resistance to breaking, which in a knife edge is usually chipping. Or, if you drop
Hmm.
your knife point first, the tip will bust off. So we want high toughness. So toughness and hardness, those are two big ones. There's usually a trade off there. Softer means tougher, but it's more
Hmm.
likely to deform. And we want a steel that is both hard and tough because we want to make the edge thinner so it performs better. The thinner the edge, the lower the edge angle, the better the knife will cut, and the longer it will cut well. So we want high toughness so it doesn't chip, and high hardness so it doesn't roll, so we can make that edge as thin as possible for high cutting performance. Uh, so the
Well, there we go. Tool steels are the best, so we can end this right now, huh? I mean,
so those are two properties. Another one is wear resistance. And the
Mhm.
higher the wear resistance, the higher the edge retention in terms of edge wear. So when you're slicing an abrasive media, the edge will slowly wear. So it goes from being a sharp, pointy triangle, so it's more and more rounded, and it's not cutting as well. It's not as sharp. So we want it also to have high wear resistance for high edge retention. But the more wear resistant it is, the less toughness you have because you need to put more hard particles in the steel called carbides or nitrides. One you might know that everyone might know about is vanadium carbides. Vanadium carbides are really hard,
Big fan.
which is why the more vanadium is in the steel, usually the more edge retention and wear resistance you have. But the more carbides you put in there, the more brittle the steel is because the carbides are really hard particles, and so they make the steel easier to break. Just those really hard particles are brittle, and the more of them you have, the more brittle the steel is. If it was 100% super hard carbide, you could drop it on the floor and it would just break into a million pieces.
So great way of just outlining all of that different stuff. I mean, basically, tool steel is the top category in all those different performance features that you just mentioned, though, correct?
The very best steels in terms of a combination of hardness, toughness, and wear resistance are non-stainless tool steels made with powder metallurgy. Now, not all of them are created equally, but they're steels
Mm-hmm.
that are designed to have only vanadium carbide. And the reason for that is, like I said, vanadium carbides are among the hardest of carbides in tool
Mm-hmm.
steels. And so if you have harder carbides, you need less carbide to get the same amount of wear resistance. So if you have a really soft carbide, like in a simple carbon steel, it just has iron carbides called cementite. They're a lot softer than vanadium carbide. So you need way more cementite to get the same level of wear resistance as vanadium carbide.
Just off the top of your head, I mean, what do you think is an estimate for how much cementite you would need to equal the same amount volume of vanadium carbide? Just off the top of your head, what do
I
you
don't
think?
even know. Maybe 3 times more. I'm not.
Yeah,
I'm not
I
sure.
mean, it's pretty intense, right? We saw on the Catra how basically all of even the stuff that had a lot more cementite, it was like, yeah, that's not really doing much.
Yeah, and there's some complications there, like how hard is the abrasive in the media that you're cutting in the Catra and stuff like that. So it depends on what kind of test you're doing. So there's no easy answer, but vanadium carbide is almost 3 times harder than iron carbide. So if we use a really simple simplification, then we'll say you need 3 times more of the iron carbide called cementite. But for toughness, the hardness of the carbide almost doesn't matter. It's more about the
Mm-hmm.
size of the carbides. So you're putting 3 times more iron carbide in there, and it has much less toughness. It's much more brittle, even at the same level of wear resistance. So vanadium carbide, you add less carbide to get the same level of wear resistance and have much more toughness because there's less carbide in there.
So vanadium boys are the best, is what you're saying, because you could use a lot less of them for the given volume.
Mm-hmm.
And if you have less volume of them, then basically it's going to be much tougher.
Right. And powder metallurgy is great because it keeps our carbides small. And another benefit of vanadium carbides is that they coarsen more slowly than some other carbide types. So molybdenum tungsten carbides in high-speed steels like Rex 45 or M4, or
Mm-hmm.
stainless steels with lots of chromium carbide, those carbides will grow more in powder metallurgy steels. Well, this is kind of backwards of conventional steels, where vanadium carbides will form in the liquid and they get really big. But in
Mm-hmm.
powder metallurgy steels, it's not about their initial formation during casting, because in powder metallurgy they spray nitrogen at the liquid steel, and the steel solidifies in these little pieces of powder that solidify almost instantly. So it's not how they
Mm-hmm.
solidify; it's how they grow later. So you take all that powder, you put it in a big can under pressure and high temperature to make it into solid steel from the powder. And then you also have to heat it up hot before it's forged and rolled out into thin sheets for knives. And during all those high temperature processes, the carbides will slowly grow. And the vanadium carbides are more stable, so they grow more slowly than the chromium carbides or the moly tungsten carbides. So vanadium carbides are almost always better than chromium or moly tungsten carbides. Another one is niobium carbides. They also coarsen very slowly, even more slowly than vanadium, and they are almost as hard as vanadium carbides. So in powder metallurgy steels, you basically want all vanadium carbide with some. There's some reasons not to have it, like ease in sharpening or grinding,
Mm-hmm.
but we don't want to
Yeah,
get
not
too
everybody's on
distracted
the
in this
bandwagon
discussion.
for. Yeah, not everyone's on the bandwagon for diamond and CBN. But that's a very interesting point that you just brought up there, where it coarsens less throughout the entire process. I mean, usually when we think of the PM process, we just think up just right there at the beginning, make it finer. But you're talking about how the heating throughout the process of even just rolling it out, you could have things coarsening, which I think is really interesting.
Yeah, and some tool steel companies have advertised that their powder is finer than competing processes, but the size of the powder is really a secondary concern. It's more about the coarsening that happens later. A finer powder will lead to slightly finer carbide size in the end, but it really doesn't matter as much as what type of carbides you have in there, and then what temperatures you're using during processing.
That's right. I mean, you pretty much debunked all that with you did something with 204P, M390, and 20 CV, correct? You did a little
Yeah,
article study.
those are all identical steels, but made by different companies. And Crucible, for example, is the first company to come out with powder metallurgy tool steels. And so companies that have newer facilities will advertise the benefits of their facilities. But the
Hmm.
carbide sizes were identical essentially between those three steels. Maybe a full statistical analysis would reveal some small difference, but just looking at them, they look very similar. And if an
That's groundbreaking too, because it's just like, oh, the third gen, it's got to have the third gen, and all the people, getting this bias about the third gen finer powder being finer structured, and then you pulled up all those micrographs and heat treated all those specimens, and it's like, oh, I guess not.
Yeah, and even I wasn't sure what I would get. I had always bought into third generation. This makes it better. Crucible steel's always going to be a little bit worse, but in terms of carbide size, no, not that you can see. The steel type matters way more. So if you then look at 4V, CPM 4V, and Vanadis 4 Extra, which are also very similar, they have much finer carbides than any of those three. Even the M390 made with third generation technology. The Vanadis 4 Extra is way finer, and the 4V again looks very similar to it. If there's any difference, it's not easily perceptible.
Yeah, that's interesting. I mean, for the people listening right now, I mean, I've got to say this, I got to ask you this so that you could just put this to rest. I mean, people are listening to this and they're like, oh my God, well, if PM steel's so good, why not just PM everything? So would you PM 1095 for the listeners here?
Yeah, I wouldn't. The reason is when you make powder metallurgy steels, they have a little bit higher oxide content. Uh,
Hmm.
and so for a steel where the carbides will dissolve at forging temperatures, it doesn't matter how they form during solidification. 1095, if properly processed, will have as fine or finer carbides than in a powder metallurgy version of the same steel. And they can make it cheaper and potentially with lower oxygen content. And it can also open them up to other processing avenues. Like there's vacuum induction melted steels or electroslag
Hmm.
remelted steels. Those are other technologies that are better at removing impurities like oxygen. And so a 1095 made with those technologies would be better than a powder metallurgy version. So powder metallurgy has specific uses. One of the best ones is making steels with more vanadium in them, and that's really where it shines.
Fascinating. I mean, that's definitely another topic for another video. They're talking about the consequences of oxides and if the oxides and the PM steels override some of the features. We're not going to go off on that tangent. I mean, your article that you just put out is what is the future of stainless knife steel design? And we pretty much just talked about here how these tool steels have better mechanical properties when it comes to achieving higher hardness, more wear resistance, more strength.
Mm-hmm.
So, why is it that stainless steel is lagging so far behind these carbon tool steels?
Yeah, so we talked about three major properties: hardness, toughness, wear resistance, that we want them all to be as high as possible, obviously. But we have a
Mm.
fourth property that we want, and that is corrosion resistance. And to get corrosion resistance, you have to add more chromium. Now, there's no fixed definition of stainless steel. You'll hear people talk about how it needs to be at least 12% chromium or something. The
Mm.
reason why 12% is more common among people that write about knife steels is because D2 has 11.5 to 12%. And so they'll say D2 is not stainless because it doesn't have the full 12% it needs to be stainless. But that is not true. So the definitions will vary. You'll see 10.5% given, sometimes 11% given, sometimes 12% given, sometimes. There's no real cutoff. More chromium usually means better corrosion resistance. And they're functional minimums for different applications. If you're in salt water, like ocean usage, you need a lot of chromium. You also need a lot of molybdenum to avoid rusting and pitting. So stainless steels, you're adding all this chromium into them, and it wants to form
Mm.
chromium carbides. You put more and more chromium in there, and the steel really wants to form those carbides. Want in air quotes. The steel doesn't have feelings, but there are thermodynamic drivers that make the steel want to form chromium carbides. And as we discussed before, chromium carbides are not what we want because they are not as hard as the vanadium carbides and they grow larger, so they're more detrimental to toughness. You have to add more chromium carbide to get the same level of wear resistance, which drops your toughness. And the chromium carbides are also larger, which drops your toughness. And another thing that we see in the microstructures of these steels is that the chromium and vanadium carbides will cluster together and they'll make larger carbides because they're connected. They connect into these weird teddy bears of carbides that are all connected to each other, and it makes the toughness go down because of it.
That's interesting. So basically, what you just said there is that this chromium is sapping the strength of our vanadium. It's stealing some of that carbon for making carbides. It's a competing resource, huh, for making the harder carbides we want.
Yeah, so if you take CPM 4V with 4% vanadium in it, it'll form about 8% vanadium carbide. If you look at the same steel with 14% chromium and carbon to go along with it, you have S30V essentially. So S30V has the same 4% vanadium, but it only has half as much vanadium carbide, but then 10% chromium carbide. So it has way more carbide, dropping the toughness, and it has similar wear resistance, maybe a little bit more. But so half of the vanadium carbide and a whole bunch of chromium carbide. So the toughness is way lower. Then if we increase the chromium even more, up to 20%, then we have M390 or 20CV. And that has about 2.5% vanadium carbide. So we've almost halved the vanadium carbide again. But now we have like 18% chromium carbide as opposed to 10 in the S30V or 0 in the 4V. Now, this is all after heat treatment. So we're greatly increasing the amount of chromium carbide, dropping our toughness, also the overall carbide volume, dropping our toughness. And the vanadium carbide we're forming keeps going down. So our vanadium is kind of less effective and our toughness is severely dropped. So you can keep adding chromium to try to improve corrosion resistance. Like 20CV is more corrosion resistant than S30V, but your toughness is now pretty bad, especially if we look back at our original 4V with no chromium carbide. It had great toughness, really good wear resistance, and then you add a bunch of chromium to it, and now the toughness has fallen off a cliff.
And for those listening, I mean, for a lot of people, they start geeking out on steel. Maybe they bought a few pocket knives and they're like, okay, this stuff is cool. Okay, these steels have chemistry. Okay, this weight percent of, say, vanadium, that means if it's got a lot of that, it's going to be more wear resistant. But what you're talking about essentially is not that weight percentage, but how much carbide is formed inside that steel after heat treat.
Yeah, you can't necessarily just look at the composition and know exactly what it's going to look like in the microstructure.
Mm-hmm.
You can't look at the carbon content and see how hard it's going to be. 15V has 3.3% carbon in it, 1095 has 0.95%, but the 15V doesn't get 3 times harder than the 1095 because
Yeah.
all of the elements interact and do different things. The 15V has all of that carbon to form vanadium carbides, and so it ends up with carbon in solution to contribute to hardness at a similar level to 1095. So when we talk about solution, that's the carbon that goes into the steel to contribute to hardness as opposed to forming with a carbide. If it's locked up with a carbide, it's not directly contributing to the steel hardness.
Yeah, and I just thought that was a important point to emphasize because I know a lot of like conversations with friends and stuff, or even just conversations on forums, people just have a very rudimentary level of understanding about this type of stuff. And so they'll hear us talking about all these different percentages of how much vanadium carbide, or you said 2% vanadium carbide and M390, and they'll look at the weight percentage of vanadium inside there and be like, oh, that's not correct,
Yeah, it's just like looking at D2 with its 12% chromium and thinking it must be stainless, like I brought up earlier, where the same steel 420 is going to have around 12% chromium, but because its carbon is so much lower, it doesn't form as much carbide, so that most or all of that chromium is in solution to contribute to corrosion resistance. So the bulk chromium content, weight percent, like you said, of 12% does not tell you the corrosion resistance. The total composition controls the final properties. And that can be difficult even for a metallurgist just to glance at a composition and say, okay, this steel is going to be like this and this and this and this.
Yeah. So concluding what we just talked about here, as far as, well, now we understand that these stainless steels are sapping the vanadium's power, so to speak. What is your solution here? We're talking about your way of designing a stainless steel that would basically make it closer to like a tool steel. And what do you think the solution is for something like that?
Yeah, so like I pointed out, the best property tool steels in terms of hardness, wear resistance, toughness combination are steels that have only vanadium carbide in them after heat treatment.
Mm-hmm.
And then you set your toughness wear resistance balance with the amount of vanadium carbide. So you take CPM 1V or Z Tough or CD1, those have 1% vanadium in them. They have really high toughness with moderately low wear resistance. On the other end of the spectrum is 15V with 15% vanadium that has really high wear resistance with moderately low toughness. And then there's steels in the middle. So 3V still has pretty high toughness with good wear resistance. 4V has a little more wear resistance, a little less toughness. CPM M4 has some moly tungsten carbides in it. It still has a pretty good balance of properties. Then there's Vanadis 8 and 10V have even more wear resistance and less toughness. So you have this curve of toughness wear resistance. On one end with low vanadium, you have really high toughness and relatively low wear resistance. On the other end, you have really high wear resistance and relatively low toughness. And the steels we're really missing out on in stainless steels are in kind of the 3V, 4V range, where they have
Mm-hmm.
moderately high to high toughness with still really good wear resistance for good edge retention in the knife. And those properties are just missing in the knife steel world. So if we could make a stainless knife steel in that property range with it being stainless, then we'd really have something special. I think we'd have a generational leap in knife steel performance. And 3V is a good example because it has higher chromium than a lot of other tool steels. Most of the non-stainless tool steels have between 4 and 5.5% chromium. 3V,
Yeah, 8%.
yeah, 3V with its elevated chromium, it's still able to put all of the chromium in solution to dissolve all the chromium carbide during heat treating. And then it has only vanadium carbide for those stellar properties. So you can elevate chromium some and still dissolve all the chromium carbide. On the other end of the spectrum are stainless steels that have different amounts of chromium. So a major breakthrough was found with the development of S90V in 1995 when they reduced the
Mm-hmm.
amount of chromium. Before it was standard to have 17 or 18% or even higher, because steels that pre-existed S90V included M390, LMAX, S60V. They all had between 17 and 20% chromium. And they discovered with S90V that if they dropped that chromium content down to 14%, that they'd get more vanadium carbide and less chromium carbide, which had given them a better toughness wear resistance balance, a little bit closer to the non-stainless tool steels. And so that was a really big breakthrough. And Crucible continued on with that path by developing S30V, S125V, more recently S35VN. And they did that all with 14% chromium because the property balance would be a little bit better. So on one end, there's 3V with elevated chromium, S30V, S90V with reduced chromium also gave better properties. So the answer, I think, is to target a chromium content in the middle. And if you balance that appropriately with other elements, especially carbon, you should be able to dissolve all the chromium carbide, or at least most of it, and make a true stainless steel, but with only vanadium carbides, or maybe a little bit of chromium carbide. And then you can get properties in that 3V, 4V range while it's still being stainless. So when I'm talking about chromium contents in the middle, I don't mean a semi-stainless or something just more stainless than what we had in the past with tool steel properties. I
Mm-hmm.
mean a true stainless. So one thing I did not explain yet is even though we have stainless steels with 14 to 20% chromium, because they have chromium carbide, they don't have 14 to 20% chromium in solution to contribute to corrosion resistance. They have more like 10 to 13%. The really corrosion resistant steels like LC200N or Vanex, they have like 14, 15%. But a normal standard stainless steel has between 10 and 13% chromium. So you don't need more than 10 to 13% chromium in the steel if you ensure with the composition and the heat treatment that all the chromium carbides will be dissolved. And you can do that through careful composition control, especially carbon content. And one example of that is 3V versus CPM crew wear. These steels are almost the same except for carbon content. The CPM crew wear has higher carbon. So crew wear has chromium carbides in it, a little bit of them, not as much as the stainless steel. 3V does not have any after heat treatment. And the reason is because the 3V has less carbon. So it is less prone to forming chromium carbides. It forms less of it. And we have to do the same thing with a new generation stainless steel. We have to carefully control the carbon content so that we have enough carbonate, the hardness we need, but not so much that we're forming lots of chromium carbides.
Now, about that 3V thing, I remember you wrote an article. Was that in the Vasco where? I can't remember. Where you were talking about the development of 3V and how initially they had chromium carbide in there, but then they found that through, what is it, cooling through the PM process, they were able to mitigate a lot of the chromium carbide formation.
Yeah, 3V was a steel designed by Vasco, which is a now basically defunct steel company. I mean, they merged into other companies, but it doesn't exist anymore, really.
Mm-hmm.
So Vasco die. Crucible made Vasco die with powder metallurgy. And what they discovered was even though Vasco die had chromium carbides in it after heat treatment, with 3V, it did not. So the powder metallurgy process made the chromium carbides easier to dissolve. So thermodynamically, meaning if you hold the steel for an infinite amount of time at high temperature, the chromium carbides will dissolve in the conventional version. But because they form and they grow large during the slow solidification process, they're much harder to dissolve during heat treatment. But because of the powder metallurgy process, the chromium carbides are really small, and so it is easier to dissolve them during heat treating. So Vasco die still had some chromium carbide, but 3V, the same steel but made with powder metallurgy, they will dissolve. And so they demonstrated that powder metallurgy could lead to easier dissolution of chromium carbide, and that is also easier to get to your equilibrium state because the carbides are smaller and will dissolve more easily.
This is mind blowing, man. I remember when I read that, I had to read that about like 3 times because I was like, what the heck? That's crazy.
Yeah, so I think that's the general thesis of what I'm saying is that we can match the performance of the non-stainless PM tool steels by making a stainless steel with all vanadium carbide. We can use less chromium because not all of it is going into solution with our current steels. So we use less chromium, between 10 and 13%. And
it's not even just less, but it's like you're balancing it out. I thought this was fascinating when you told me this, is because usually people think everything in the steel world for knives tends to be more, 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 keep adding more. Well, you have such a intimate understanding of how all this stuff works that you can realize that, hey, adding more to this, banging your head against a wall is not going to make this better. Why not look at how much you actually need to make this work and work good, so you're not trading off everything else looking for a feature of just making the overall steel better by just adding tons more when it's not going to make everything better.
Yeah, and there's lots of stuff you have to balance there. Like the higher the temperature is that you heat treat the steel, the more carbide you will dissolve. And so, if you heat treat at a hot enough temperature, you can get more chromium carbide to dissolve. But how hot do you want to go? Furnaces have limits. Some people have older furnaces that only get up to certain temperatures, like 2,000 degrees. So how hot can you go when you're designing the steel? That matters a lot. How much corrosion resistance do you need? So do you want to do one with 10% chromium in solution or 13% or somewhere in between? You'll be able to add more carbon in if you're on the lower chromium side and still dissolve all the chromium carbide. So you'll be able to get more hardness, which we might want. Maybe S30V corrosion resistance is plenty for most people, or 154 cm corrosion resistance. Like if we match that, it'll be plenty good enough, but maybe we should lean on the higher hardness side for better performance rather than just corrosion resistance. Or maybe you can make two different versions, one super corrosion resistance version and one average, but for higher edge performance. There's different directions you can go in.
Excellent. So just to recap what we just talked about here, essentially the path to the ultimate stainless steel improvement is balancing out carbon chromium, getting the stainless feature, but then also keeping the carbides focused more on making the carbides we want, the vanadium type. PM process as well helps with that. You talked about, while we were talking here, generational leaps when you were talking about how they went from S60V to S90V. And I think you've talked about that before, where you kind of have this in your head, this generational leap forward type thing. I mean, what do you think is the first, second, third, and where we're at now with the whole generational thing that you've defined? Generations, and when I think generations, I think, okay, first gen powder metal, third gen powder, and we kind of like debunk that as like having any difference. That was just a manufacturer type thing. But I thought you had a cool little thing there where you were talking about how these generational leaps, and it seems to be something that you've defined. I mean, what are the different generational leaps? What does it take to have a generational leap? Where are we at now? Where have we come from?
Yeah, I think S60V to S90V was a generational leap. They got better toughness, better wear resistance at the same time, and better corrosion resistance. And they did that all by reducing the chromium and having a better balance with carbon. And I think we can do the same thing. It's really simple when you just dilute it down to one idea. Just reduce chromium and then balance the carbon to go with it. And the closer we get to those tool steels, the better the performance can be. And I really think it's possible. So we did this with a non-powder metallurgy steel that we've been calling Niomax. And Niomax is all niobium carbide. It doesn't have any vanadium additions. But in that steel, we used a little bit lower chromium content than normal. And then we balanced the carbon. And in that steel, we can dissolve all or most of the chromium carbide. We use a normal heat treating temperature of about 2050 degrees. And I couldn't really detect any chromium carbide. There might have been a tiny bit of it, but not enough to really make a big difference. Now, with the powder metallurgy steels I'm talking about, vanadium is a lot more finicky than niobium. And balancing it along with carbon and chromium is a lot more difficult. Niobium actually is pretty easy because it's a really strong carbide former. It's not really affected by chromium additions that much. Even if you have lots of chromium, if you add niobium, you'll get niobium carbides to form. Unlike vanadium, where you keep adding chromium and the content keeps going down of the vanadium carbide. Niobium, you can have 20% chromium in there. You add 2% niobium, you get 2% niobium carbide.
And that's just because of chemistry thing, right? Where niobium just doesn't fit inside of the chromium carbide unit cell. It doesn't have any affinity for it. Not like vanadium, which is like, oh, okay, I'll come over here.
Yeah, it's just not really influenced by the chromium. So you can rank carbide forming elements in terms of how strong a carbide former they are. So titanium is really high up on the list. Niobium is down a little bit, then vanadium, and then a lot further down is chromium. But you get so much chromium in there, and it acts like a stronger carbide forming element just because there's so much chromium. And the stronger it is at forming carbides, the higher the temperature it wants to form and the less it's influenced by other elements. And so niobium is what I'd call a really strong carbide former. So it'll form carbides even when there's a lot of other junk in there, like a whole bunch of chromium.
And again, we have to point this out. This is difficult to bring up to people when you talk about carbide forming strength, that this is not carbide hardness, but it's strength at wanting to make carbides.
Yeah, there's terms that can get confusing. We're talking about strength of the steel and strength of carbide formation and hardness of the carbides. And so maybe there's a better term I could use, but strength of carbide formation is a pretty standard way of describing it. So that's what I'm going with. But yeah, it's important to keep in mind that the strength of the carbide formation is not necessarily related to the hardness of the carbide. Though titanium, niobium, vanadium carbides are all high in hardness, but that's more coincidence.
I see. Now, are there some detriments with niobium being a strong carbide former, like especially if we're not using a powdered process? Like if I just wanted to make some super high niobium content steel, I mean, am I going to have fine particles, or what are some detriments you think?
Yeah, because it's such a strong carbide former, when you start adding insignificant amounts of it, the carbide will form at really high temperature in the liquid. And the higher the temperature where the carbide forms, the larger it will grow. Just diffusion is faster in that liquid, the higher the temperature is. The best is to form carbides in solid steel, where diffusion is much slower and growth is much slower. But you add a few percent niobium, a lot of times you're limited to about 2-3% before those carbides just really start to blow up in size. They get really big. And it's such a problem that you're also limited in powder metallurgy steels because they will form in the liquid steel before it ever goes through the gas nozzle to be sprayed into powder. And so if it's already formed in the liquid, uh, they're going to be big carbides even after being turned into powder. And it can also be a problem just for manufacturing, even if you want to ignore that, because the carbides are little solid particles in the liquid. And so you're trying to go through this small nozzle and it'll clog it up because you're getting this solid formation in there when what you want is a liquid to pass through that nozzle. And so we would also like to use niobium in powder metallurgy steels because it's a strong carbide former. We can almost ignore the chromium to some extent because they don't interact really. But you're limited to about 2 or 3% before it starts to clog your nozzle in powder metallurgy. And no, that's not a euphemism.
It's like trying to atomize maple syrup.
Mm-hmm.
But I mean, this is the reason why we haven't seen like S90NB is just because they're just so limited with these properties.
Yeah, the
Is that
closest
correct?
we have is S110V, which was a modification of S90V that has 3% niobium in it. And that, as far as I know, is the highest niobium content powder metallurgy steel that is produced. You probably can't go much higher than that. In fact, the patent says 3.5% niobium, but this final version that they produce is 3%. And I haven't been able to find a reason talking to anybody, even the person that patented it can't tell me why they dropped the niobium content, but I suspect it's because they were either afraid of manufacturing problems or they experienced some mild ones and said, hey, we got to dial this back a little bit.
Interesting. So, I was always kind of curious, like, how the heck did they get that much niobium inside of the S110V, especially if that's kind of like the limit? I guess they must have found some sort of technique or something to figure that out. Or...
Well, they probably go as hot as they can in the liquid. There are limits. If you go too hot, then the ceramic lining, like the refractory that they hold the liquid steel in, it starts to go. It's eroding away at that refractory, which you don't really want refractory in your steel. And also, you have to replace it more often. It gets expensive. If you have a breakout, like your refractory fails, that's a big issue in manufacturing. So, there's a line or, some kind of gradient where you really don't want to go any hotter. So I imagine they're going as hot as they can, technology-wise, to do S110V. And we see this in a patent for CPM 15V as well, with its 15% vanadium, because in the original development of 10V, they tried higher and higher levels of vanadium, but if they went higher than about 10%, then they would start to get large carbides because they would form in the liquid, and that's why they ended up on 10V. But later, they tried new refractory or at least higher temperatures and saw, okay, we can push this a little bit further, and that's how we ended up with CPM 15V. So that's as high as they could go in vanadium content before the carbides would start to grow in size by forming in the liquid. So S110V, they probably do something similar, but I haven't asked.
That's really fascinating. I mean, it leads the question of, okay, well, you guys know you can get that much niobium in there. You guys know that this has some benefit with not having preference to help form chromium carbides. Why haven't we seen more, you think? I think you talked a little bit about niobium 3V.
Yeah, there was a patent on a modified version of 3V that came out right before Crucible's bankruptcy when their new development really slowed down. And they replaced most of the vanadium with niobium. And that made the carbide smaller, again, because the niobium coarsens more slowly than vanadium carbide. And so they had enhanced toughness in this modified 3V versus the original 3V with only vanadium. And We also have a little bit of niobium and S35VN and the new S45VN, and there's 1% niobium in the SPY 27 that's exclusive to Spyderco.
Mhm.
And so Crucible's been using niobium, but not up to the level of S110V. Maybe they feel 0.5 or 1% is enough to give some refinement to the structure, because that has been shown in some research. Like K490 is a non-stainless tool steel made by Bowler, and in their patent, they said that adding 0.5% niobium refined the overall carbide structure and improved toughness. So they may be using that small niobium addition for similar reasons in those crucible steels. But I don't see much reason not to go higher. Why not just add 2 or 3% to everything, just for your improvement in structure and reduction in chromium carbide. So just dial it up a little bit.
Now, I remember like 5, 6 years ago, people were talking in endless forums about niobium carbides are harder, vanadium carbides are harder. Which one's harder?
Vanadium carbides are probably a little bit harder. I've seen some references in literature saying they're equal in hardness, or even some claiming that niobium carbide is harder, but that seems to be mostly from companies selling niobium. So I think niobium carbide is probably a little bit softer than vanadium carbide. I don't know if it makes a real functional difference. There's not
Mhm.
enough research to know, at least not that I'm aware of. So I think they can be more or less interchangeable for wear resistance, but it'd be fun to see the study where they really figure that out. Can 10% niobium carbide lead to the same wear resistance as 10% vanadium carbide? And I don't know that. Maybe there's a good study out there I haven't read.
Yeah, I mean, we most certainly know they're better than chromium carbides, and finer is always better.
Hmm. Yeah, these knife edges, they're on micron scale. So the smaller we can get those carbides, the better our edge performance will be, the better our toughness will be, the better grinding and sharpening performance will be. So as fine as possible is really better, in my opinion.
So essentially, using niobium as some sort of carbide refiner. I mean, what about nitrogen steels? I mean, how does nitrogen come into play? I mean, 2017, 2018, nitrogen seemed like it was a big deal. You had people talk about how nitrogen is the future. You didn't really have people understand what nitrogen was. They were basically thinking it was like electrolytes in Gatorade. It just made it better, but they didn't actually understand how. So, what are your thoughts on nitrogen steel and the future of stainless?
Okay, so nitrogen acts very similarly to carbon in that it forms hard particles, only we call them nitrides instead of carbides. It also increases steel hardness when it's in solution, in the same way that carbon does, though you need more nitrogen for the same amount of hardness. The real benefit of nitrogen, though, is that it does not affect corrosion resistance as much as carbon does. So it's less likely to decrease your corrosion resistance, in large part because it's less likely to form nitrides than carbon is. So you can add more of it to get a hardness bump without forming chromium nitride. Uh, and it can also improve corrosion resistance a little bit by being in solution. Nitrogen can. The other thing nitrogen does is that nitrides coarsen more slowly than carbides. So Vancron is very similar to a steel like 10V or Venatus 8, but it has a lot more nitrogen in it. It's kind of like half nitrogen, half carbon, as opposed to all carbon in 10V and Venatus 8. So the Vancron has finer carbides than 10V or Venatus 8 because they're nitrides or carbonitrides, if we call them a combination of carbon and nitrogen. And in Vanax, which is a stainless nitrogen alloyed steel with really high nitrogen and a pretty low amount of carbon, it also has significantly finer particles than a comparable steel with only carbon. So if we compare Vanax to LMAX or S30V, the particle size is much finer because the chromium nitrides and vanadium nitrides coarsen more slowly. So the particle size is finer for better toughness, and it's less detrimental to corrosion resistance. But there are limits to adding nitrogen also. So Vanax and Vancron, they atomize the steel and they have the powder, and then
Mhm.
they nitride the powder to add nitrogen to it because liquid steel can only soak up so much nitrogen. So you have to do these extra expensive steps. But even when you add in as much nitrogen as you can get into the liquid steel, you can see improvements in the carbonitride size and also corrosion resistance. So you can pump in a little bit of nitrogen to improve properties. And we see that already with steels like S30V. That steel came out back in 2001, and it wasn't known until fairly recently that there was 0.2% nitrogen in there. But it does. So they added nitrogen to improve the overall properties a little bit of S30V. And I think it's a good idea to add a little bit of nitrogen in there. You might be able to also do nitrating of powder depending on what company you are. I don't know if Udahome has any current patents on that. The technology goes back a few decades, like to the 80s. So you can probably use that, but it's an extra step which adds extra cost. And it's nitrating itself is not that expensive of a process, but any extra step is going to add cost. Adding logistics into a steel mill is not a great way to reduce your costs. So, but
Yeah,
it's
those
an
are definitely the most expensive steels I've ever worked with, the Van X and the Van Cron. I mean, it seems like such a simple step, and I think I've talked to you about this before, where I was like, why is that so expensive? You're just nitrating the powder. And I thought you explained it really well. I mean, why is it so expensive, you think? Why is that such a complex process?
Yeah, it's hard to say exactly. It could just be that Udahome has really expensive steel, which they do. Uh,
Mm.
but man hours are your most expensive thing. Adding in extra time, especially if you have a process, like let's say you atomize your powder and it goes straight into a steel can and you weld it up and it goes on to the next step. Instead, you take it out of the steel can, you put it into your nitriting setup, you nitrate it, you then put it back into a can, and then it goes into the regular process. Then it really disrupts your regular production. And when a steel mill doesn't want to do a step, they charge a lot for it. And so that is my guess about why it's so expensive. Udahome's expensive already, and it's just extra logistical nightmare that they probably have to deal with.
I like it. I can get behind that.
One side note, some steels are called nitrogen steels that really shouldn't. Uh,
H1. Ah.
H1 is a big one. So its spec sheet has a nitrogen maximum on it. But people took that and ran with it like H1 is a nitrogen steel, but it only has trace nitrogen in it. The steel company is not adding any. They don't want any in there. So you should not call H1 a nitrogen steel. So it's a type of steel called an austenitic stainless, and those steels typically have nitrogen maximums on them, which is why nitrogen's listed in the composition. But a lot of composition charts don't list that it's a maximum. They just list it as like 0.1% or whatever it is. But it doesn't have 0.1% in it. It has half of that or even less. Then a steel being called a nitrogen steel, even then that varies by a lot. So a steel like Nitro V or BD1N or 14C28N, they have like 0.1 or 0.11% nitrogen, which was a pretty small amount, as opposed to Van X, which has like 1.5%. I mean, they're not even in the same category. So
Well,
you
hold
could
on a
take.
second. What about Nitro Cut? 4116N? Come on, man. That's got to
Well,
be a nitrogen steel.
you're just trying to look impressive by bringing up obscure products now, Sean.
Well, I just mean that's just like, I was being sarcastic or facetious. I mean, that's just like the lamest steel I've ever heard of, where you take the 4116 and you put nitrogen in it. Like,
Yeah, and a lot of those steels, if you take the nitrogen out, they behave more or less the same. They'll get slightly lower hardness when you heat treat them, but it's not radically changing the microstructure of the steel or how the steel behaves. It's just got a touch of nitrogen in it, which might help you out as a steel designer if you're trying to dial things in. But Van X is a completely different steel than LMAX because it has way more nitrogen with a lower carbon ratio. But BD1N is a small tweak on BD1, and 14C28N is relatively small modification of 13C26.
so, I mean, would you probably narrow down the list of nitrogen steels to just LC200N, Nitrobe 77, Vanex, and Vancron? I mean, would that be would that be
Yeah,
fair?
yeah, those are the big ones off the top of my head. There is a murky middle, like the S30V with about 0.2%. So what is the definition of a nitrogen steel? I don't know. Maybe
Hmm.
the easiest definition is just that you intentionally added it. Obviously, if you're not intentionally adding it, do not call it a nitrogen steel. Like H1 would not fit any definition of a nitrogen steel. But even then, you have to understand that there's a range, and some steels have only nitrogen in them, and some steels are mostly carbon with a little bit of nitrogen, and so those are not in the same property category. They're not really similar at all.
Yeah, maybe it's if it's not forming nitrides and doesn't have nitrogen in solution, making like a nitrogen martensite, maybe it's not a nitrogen steel. But I guess that would be still blurry for S30V, right? I mean, maybe some of that nitrogen's making some carbonitrides, maybe some of it's going in solution. I mean, it's kind of messy. It's never a super clean process with these things, huh?
Yeah, it was probably better if no one asked me to set a definition for it, and of course, no one's asking me. So.
Okay, I won't ask you. So, concluding here about nitrogen steels and if they are the future, I mean, I think you've kind of maybe spelled that out where, yeah, there's some really cool properties to chase there, but the cost would be so extreme that that's probably not going to be anything in our future unless it's a lot more widespread for some use that's actually making the money and not knives, huh?
Yeah, if Udahome makes more of it, it'll just be more available. That'll help. Another issue with Vanex is that it still has like 9 or 10% chromium nitride in it. And just like we were discussing, softer carbides or softer nitrides, that doesn't help your toughness because you need more of those particles to get the same wear resistance. Vanex has a lot of chromium in it at 18%. About 14 or 15% of that is in solution. So an improved Vanex, in my opinion, would have that dial down the chromium to about 14% or so. Drop the carbon nitrogen as well, and try to get as little chromium nitride as possible. So if they could do that and bring the cost down, they'd have something really awesome. Basically that generational leap that I'm talking about. But I don't know if they're looking at that. So that's what they should do.
I don't think so. I mean, what they did, Vanex 35 and then Vanex 75, and they kind of, I don't think they took your advice about dropping the chromium.
Yeah, they seem to like that 18% chromium level. I wish they stopped doing that. But yeah, Vanex, the current version, is relatively recent, so it'd be a surprise if they came out with a new version anytime soon.
So 2 points you just brought up, and I just want to hit those real quick, is that one, we don't necessarily need nitrogen to get finer particles like we would want. And then two, these nitrides are actually a little softer than carbides.
Yeah, maybe the literature is mixed. Measuring hardness on tiny particles is difficult. So, it's not like there's one agreed upon value for the hardness of every carbide and nitride, but the nitrides might be a little bit softer, but sometimes they're also smaller, and smaller can show up as less wear resistance in certain wear resistance tests. So, nitrogen is not the answer to everything. It's not like nitrogen turns everything into a super steel. You could make a new generational leap stainless steel with very low amounts of nitrogen or no nitrogen at all.
Interesting. But as far as making a generational leap, you would probably use some of that nitrogen just like you'd be using the niobium to help refine things just that much more. Is that correct?
Yeah, M390's got 0.2% nitrogen in it. S30V has 0.2%. So it doesn't seem to be a big problem for adding it. Might as well use that nitrogen so that you can have a little bit better hardness corrosion resistance balance.
I love it. All right. So we've covered wear resistance, we've covered particle size, we've covered carbide types and hardness and what we want. So the last thing is that, well, stainless steels don't actually get as hard in the matrix. I mean, we've got these carbon tool steels, they're pushing 65 all the way up to 70, peaking out the hardness HRC. And then stainless steels, you got them coughing their way up to 64, 65. So what's going on with that?
Yeah, there's a few things that affect that. I do have an article on why Vanex doesn't get any harder because it tops out around 61 Rockwell, whereas other stainless steels can get up to about 64 or so. And so one limiting factor is retained austenite. And I don't know how quickly I can describe this, Sean, but you add more elements into solution in your steel, and the austenite becomes more stable. So the temperature where martensite forms, you heat it up to high temperature and you quench it to room temperature, like in oil or water. And when you quench it really fast, you get martensite formation. Martensite is your hard phase in steel, and there are temperatures at which it starts to form and finishes forming. And so your martensite start and martensite finish, you'd like to be high so that you have full martensite formation by the time you get to room temperature. But the more carbon and chromium you have in solution, the lower those formation temperatures are, and they'll even go below room temperature, which is why people do cryogenic or cold processing after quenching so they get more martensite formation. But at some point, even cryo is not enough to get you more martensite, and you'll still reach some limit. So VanX, it tops out around 61 Rockwell, in part because it has so much chromium in solution for corrosion resistance. So it gets that high corrosion resistance from the high chromium in solution, but its hardness is reduced relative to some other stainless steels because of it. So on the other end, you can have tool steels, which only have 4 or 5% chromium in solution, and they can really go up high in hardness because they don't have as much of that retained austenite bringing down hardness. So again, austenite is your high temperature phase. You heat it up hot to austenite, you quench to martensite, and what's left over is the retained austenite, which is a soft phase versus the hard phase you want, martensite. So we have another trade-off here between hardness and corrosion resistance, where you can have a really high corrosion resistant steel like LC200N or VanX, but they're not going to be harder than about 60 or 61 Rockwell. And if we went even higher on corrosion resistance, then it'd be even lower in hardness, 55 or something. On the other end, we have tool steels that get up to 67, 68, but they're not stainless at all. And then we have a bunch in the middle, like S30V, that get to about 64 Rockwell with moderate corrosion resistance. And so that's another balance you have to use in design is, do you want super high corrosion resistance with pretty good hardness? And also, it's more difficult to heat treat those. You really have to dial in your practice and use cryogenic processing to get 61 Rockwell on VanX. If you're doing normal factory heat treat, you might be 58, 59. Or you can go, borderline stainless corrosion resistance and get 65, maybe 66. Or you can go somewhere in the middle. So that's another trade-off that you're going to have to fight with in designing a stainless steel. So how hard do you want to get it versus how corrosion
And that seems
resistant
like the
it's going to
most
be?
interesting challenge of all when it comes to making a stainless steel that can overcome that challenge. I mean, what you're basically saying is that the more of these dissolved elements you put in there, they basically cause some interference for getting the steel as hard as you would like when you quench, per se.
Yeah, so stainless design is just another set of trade-offs. When we had non-stainless tool steel, we had hardness, wear resistance, and toughness. Now we're adding in a fourth thing, and adding in a fourth thing just really ramps up your complexity. So before we had toughness versus wear resistance, where we were adding in more carbide for wear resistance, but that dropped our toughness. Now we also have hardness versus corrosion resistance. And adding in more chromium makes it more prone to form chromium carbides, which is reducing our toughness for a given level of edge retention. So we're just adding in more and more things we're trying to balance, and there's not ever going to be one super steel which is as corrosion resistant as VanX and get as hard as 15V or Rex 121 and be as wear resistant. You can't do it all at the same time
Yeah, I
and
was
be
gonna
as
say the
tough
toughness
as
thing is a
3V.
is the big deal, right? It's like, oh, maybe with the ferrotitanite WF, but it's like toughness. Nope, that's been completely bottomed out. That's gone.
Yeah, so we maximize that balance by using vanadium carbide and carefully selecting our amount. But to get beyond that toughness wear resistance balance of vanadium carbide only steels, that would require another leap in something, and maybe it's not possible. You might get a little bit finer carbides and niobium carbides or something like the modified 3V, but we're not going to shoot up to the stratosphere with 15V that is as tough as 3V.
So both of these types of steels can get retained austenite, but stainless steel gets retained austenite due to these elements and then carbon steel do to those elements? I mean, what's the main element you would say for stainless steel that causes a lot of the retained austenite from putting lots of stuff in solution?
Well, the main one for any steel is
Oh, it is.
carbon. So, you can get quite a bit of retained austenite even in non-stainless steels, and you have to avoid it. You can heat treat D2 without cryo and heat treat it wrong, which is a non-stainless steel, and have it be all retained austenite because you heat treated it too hot. Retained austenite and carbide anyway.
Hmm.
But with stainless steels, because you're putting in so much chromium, chromium's not the most important element for retained austenite. But if you add in 12% of it or 15% of it, then it does become very significant. Just you have so much of it that it's really reducing your martensite formation temperatures. And that's why stainless is a little bit more finicky in designing them. Some steels are still not that difficult to heat treat. Some people think stainless steel is way harder to heat treat than some other steels, and it's not really true. But a steel like Vanex trying to dial in a 61 Rockwell heat treatment, it can be challenging.
Yeah, I mean, that is very interesting that you bring that up as far as like the stainless steels not being as challenging as some of these carbon steels that require all these normalizing and all these different features for shrinking the carbides versus just the stainless steel is just, well, put it in the oven and there you go.
Yeah, the real nice thing is that you don't have to quench super fast. So these low alloy steels that need a water quench or a fast oil quench, as opposed to most stainless steels, you can even leave them in air and they'll fully harden. Or a lot of people like a plate quench where they put it between two aluminum plates, and that cools it plenty fast for full hardness. But yeah, so hardness, corrosion resistance, that's another difficult balance. I didn't really cover it in the article, so it's good that we talked about it a little here.
Yeah,
I think
most
really the
definitely. I mean,
bottom line is, we need stainless steels with less chromium in them. That's the bottom line. That's the big secret. We need less chromium in our stainless knife steels.
balance it out. Find that happy balance. You've
Mhm.
already defined basically how much you need for it to be stainless, and then trying to put more is going to cause more detriment. I think that's interesting too that you brought up how well carbon is also the big influencer of causing retained austenite. I mean, how much carbon you need to put in solution versus chromium in solution to cause lots of retained austenite? Is it like close to 1% for carbon, and then for chromium, what is that, like 13?
Yeah, it all depends on your balance. I mean, if you're over about 0.6% carbon, no matter what your chromium level is, you're going to start getting some retained austenite. 1% carbon is quite a bit to have in solution. 0.6 is normally where steels top out, maybe zero point 0.7 or zero point 0.8. But that's a lot of carbon. Then your toughness really starts to take a dive at that point, even without much carbide in the steel. But if you've got 15% chromium, then you probably can only have maybe 0.35% carbon in solution before you're reaching your limit on retained austenite, even with cryo.
That's significant, man. I mean, no one really thinks about it like that. They just see any amount of chromium in there and they think, oh, it's bad. It's not going to be as fine structured. Up, it's going to have more problems. And I mean, I think a classic example of that is the whole 1095 versus AEBL argument that people will say they'll look at the two steels, they'll look at the amount of carbon, and they'll look at the chromium, and they'll be like, "Oh, that's going to be problematic. That's going to be coarse structured. This one's going to get harder. It's got more carbon." But then you brought up a really fascinating point there, where it's like, well, you're only really topping out zero point 0.6 of that carbon into solution. So you're not even using all that carbon in 1095. That's not what's making it hard, per se. The full Monty, the 1%.
Yeah. Yeah. I mean, a 1060 steel, so that's the same as 1095, but with 0.6% carbon instead, that can get up to, 65 Rockwell or thereabouts. So that extra carbon mostly goes towards carbides. That's what it's added for. And so, yeah, when we're designing a knife steel or a stainless knife steel, we're specifically targeting different amounts of carbon in solution versus a given amount of chromium in solution. So, we want to be around 0.4% carbon in solution, usually. That's a good balance of high hardness, like 63, 64, and also good toughness.
Man, we could talk about this type of stuff like on and on, but we'll probably wrap it up right about here. Really fascinating stuff. I mean, love your work, love the article. I mean, you really just nail it. I mean, I wish there was somebody like you in the right place to get a lot of these features just put in.
Yeah, I think knife steel business is not that large. And when they design these stainless steels, it's like for plastic mold steel. And I think, that market's only so big, and their needs are not the same as for knife steels. There's a lot of overlap, which is why we have good steels out of there, like S90V or M390, which have worked well in knives. But, Crucible is really the main company that has designed steel specifically for knives, and they're doing great. But maybe these companies can come out with something a little bit better. Again, what we really want is like that generational leap in performance, where we get something close to or at the level of properties of those non-stainless powder metallurgy vanadium alloyed steels, uh, but get those same properties in a stainless. I think it's possible. I really think it is.
Well, it looks like you're the man that's figured it out. Fantastic, man. All right. Take care.
Thanks, Sean.